Hello, my name is Kai Takeuchi, and this is my Physics 1 Lab 3 Black Hole and Orbits. In this lab, we will find the mass of the black hole and generate a model of gravitational interaction of a star with known mass and a black hole, find the initial velocity of the spaceship for takeoff on a planet near the black hole, and create a trajectory for the spaceship to orbit the black hole and escape the system without crashing into the black hole or planet. All of this will be done on GlowScript. The physics principles covered in this lab are Newton's second law, specifically the momentum principle, the velocity update formula, and the position update formula. For the gravitational force, we use negative Fg equals negative Gmm over r squared times r hat. The other principles used were the perpendicular and parallel components of Fnet. Seen here, the Fnet of the parallel is dp dt times p hat, and the Fnet perpendicular is p times dp dt. And Fnet here is the parallel component added to the perpendicular component. The free body diagrams for the two separate parts are seen below. On the left side, the system is the star, the surrounding is the black hole and the universe, and the arrows point towards each other. For the second part, the system is the planet and the spaceship, and the surrounding is the black hole in the universe. You can see where the arrows are pointing and how they interact with each other in the bottom right diagram. For the first part of the computational model, here's the code that I used for the GlowScript. In the top left was the first lines that I edited. All of these formulas were derived by using the principles stated in these slides before, specifically the parallel and perpendicular net force formulas. Here's the result of the first part. As you can see, there are 3 arrows pointing towards the planet at all times. The perpendicular, the parallel, and the n hat arrows are seen here. The results were that the mass came out to be 1.39 times 10 to the 34 kilograms. The Fnet was 9.86 times 10 to the 28th newtons, and the Fnet parallel is 3.61 times 10 to the 28 newtons, and the Fnet perpendicular was 9.09 times 10 to the 28. Here is my code for the second part of the problem. This is the one where the spaceship will be orbiting the 2 separate planets. This one was a little bit more challenging because we had to find the initial velocity of the spaceship, the initial and final, and trying to not get the spaceship to crash into the planets. Here we also used the formula stated on the physics principle slide to derive. The results for this section of the lab can be seen on the left here, where the spaceship, the path is represented by the purple line. The moon that orbits the planet is the turquoise line, and the planet is the blue ball. The initial velocity came out to be negative 4.7 times 10 to the 7, 3.2 times 10 to the 6 in the y direction, and 0 meters per second in the z direction. The shortest distance came out to be 1.36 times 10 to the 10 meters. For the what does it mean question, I came out to be that the rate of change of momentum and net force in this context is the parallel and perpendicular forces that are acting, or forces of this planet. For the what if part 2, I calculated it out, and I'm not entirely sure if this is correct, but my x component of the ship's speed came out to be negative 1.5 times 10 to the 6, and the y speed was 1 times 10 to the 7th, and the z direction was 0.